Hello class, today I'm going to present everything you need to know for the AP test of chapters 18 and 19 of the book, which are electric currents and DC circuits. So in the previous chapters we studied static electricity, so electric charges at rest. In this chapter we're going to study the motion of electric charges, which we're going to call the flow of electric charge, we're going to call current. So in the 1780s, this professor at the University of Bologna, which Luis Galvani, he carried out a series of experiments with the frog's legs, analyzing its contractions, and he claimed to have found animal electricity, thus claiming that animals produce electricity that are responsible for certain movements. However, later, Volta, who was a professor at the University of Pavia, he was skeptical of this conclusion, and he thus experimented with it himself. And he found that it wasn't the animal itself that produced the electricity. Instead, it was the contact between the similar metals. So he realized many experiments. So he then realized that a point of moisture, or a moist conductor, at the point of contact between two dissimilar metals was necessary for an electric current to be produced and for a battery to be effective. Keeping this in mind, he designed the first model and made the first battery ever, which is the one shown here. So a battery produces electricity by transforming chemical energy into electrical energy. The simplest model of a battery, like today millions of types of batteries exist, but the simplest model of one is shown right here. So it consists of two dissimilar metals, which are the rods that we see right here, and these are called the electrodes. And the electrodes are immersed in a solution called the electrolyte. In this case, is the sulfuric acid. And this device is properly called an electric cell. And technically, a battery is made of many electric cells, but today, like if a flashlight battery is just one cell. So it can be very simple. A very simple cell can work as a battery, but in order for it to be more effective, then it has to be created of many different cells. These chemical reactions are formed because one of the electrodes is dissolved continuously by the electrolyte, and therefore losing electrons. And when this loses electrons, the other one loses protons because it gives them out to the other one, and therefore this is why the chemical reactions occur. And then the terminals are the parts of the electrodes that are outside the electrolyte, and this is where the wires are connected and where everything, when the electric current is transpassed. And if you connect, for example, the negative terminal of one cell to the positive terminal of another cell, and so on, you create a series circuit, a series battery. And these are the most common types of battery today, and this produces a bigger and more effective battery. And when you do this, when you connect many cells together and you form a battery, then you have to know that this series battery that you're creating, the voltage of it's gonna be the sum of all the voltages of the cells. For example, if you have two 1.5 voltage cells put together, the total voltage of the battery is gonna be 3.0. Or if you have four cells, each one containing one voltage, 1 volt of voltage, then the voltage of the battery is gonna be 4 volts. And right here in this figure, we can see a diagram of a flashlight battery of a dry cell. This is, for example, a AA battery, the one you use for remote controls or for anything really. And that's in figure A. And then in figure B, we can see two AA batteries piled up together, forming a series battery that is what is normally used for the flashlights. So that was section 1, and now section 2 is electric current. So the purpose of a battery is to produce a potential difference, and this can make charges move around. So when a continuous conducting path is connected between the terminals of the batteries, between the positive terminal and the negative terminal, we create an electric circuit. This is shown in figure A. And in figure B, we see the diagram of an electric circuit. So we can see that this symbol represents the battery itself, and then battery voltage can flow throughout the whole battery as long as it is continuous. And anything can be connected to this battery. It can be a light bulb, a heater, a radio, whatever. In the test, it's not really going to matter because everything follows the same theory. And in this circuit, any flow of charge is called an electric current. Or more precisely, the electric current in a wire is defined as the net amount of charge that passes through the wire's full cross-section at any point per unit time. And there's an equation to find the unit, and this you're going to want to write it down, which is that current is equal to change in charge over change in time. Or I equals to change in Q, delta Q over delta T. Electric currents are measured in units of coulombs per second, and these are given a special name that are the amperes. So 1 ampere is equal to 1 coulomb per second. And in order for a current to flow, it has to be in a complete circuit, which is a circuit that is closed at both ends and it is continuous throughout the whole circuit. And if it is not continuous and it is not complete, it's an open circuit. And in this circuit, no current is going to flow. But in a continuous circuit, then the current that flows is going to be the same for the whole circuit at any point in the circuit. And this is because of the law of conservation of charge, which says that a battery does not create or destroy any net charge. So now let's take a look at example 18.1. So current is the flow of charge. A steady current of 2.5 amperes exists in a wire for 4 minutes. A. How much total charge passed by a given point in the circuit during those 4 minutes? B. How many electrons would this be? So first, for the first one, we're going to want to know that they ask us at any given point, meaning that the current is always going to be same. And because of this, we can infer that it is a complete circuit. So in this problem, they give us the electric current, which is 2.5 amperes, and the time, which is 4 minutes, and they want us to find the charge in part A. So the first thing that you need to do is that you have to know that delta T is given in minutes, but we work in seconds. So 4 minutes is the same thing as saying 240 seconds. And then we're going to use a simple equation that current is equal to change in charge over change in time, and therefore change in charge is going to be equal to current times change in time. Therefore, it's going to be equal to 2.5 times 240, and that is going to be equal to 600 coulombs. And as simple as that, we find the answer to part A. And then in part B, they're asking us to find how many electrons. And we know that an electron consists, the charge of an electron is 1.6 times 10 to the negative 19 coulombs. And therefore, we're just going to divide the charge, which is 600 coulombs, over 1.6 times 10 to the negative 19 coulombs, which is the charge of an electron. And this is going to give us the number of electrons, which is 3.8 times 10 to the 21 electrons. And that, as simple as that, we have solved example 1. So then we go to conceptual example 18.2. So they ask us, what is wrong with each of the schemes shown in figure 18.7, which are these pictures shown right here, for lighting a flashlight bulb with a flashlight battery and a single wire. So let's first take a look at A. Here, as you can see, there's no closed path, and therefore the current will not flow. And this is what's wrong with this. And B, we can see that there is a closed wire, so it is a complete circuit. However, we see that the wire only touches the positive side, the positive terminal of the battery, and it doesn't touch the negative terminal, and therefore it is not a complete circuit. And in example C, we can see that there is nothing wrong with this current, with this diagram, because this is a complete wire closed, touching both terminals, and therefore this will light the light bulb. So in many real circuits, wires are connected to a common conductor to provide continuity. This common conductor is called ground. which is represented by this symbol. Sorry. And like in reality, in buildings and houses, the ground conductor is connected to the ground, and in cars, the ground conductor is connected to the frame of the car. However, in the circuits that we're gonna be watching in this chapter, we're not gonna be working too much with conductors. Also, in chapter 16, we saw that conductors contain many free electrons moving around, and this happens too in the circuits. Many electrons are moving freely through the circuit. For convenience purposes, we're gonna set the directions of current. So mostly, in most cases, the direction that the charge is gonna move is gonna be the positive direction. And if we're talking extremely specifically about electrons, they're gonna be moving in the electron current, therefore in the negative direction. So that was it, for example, for section 18.2, and now we're gonna go to 18.3, which is Ohm's law, resistance and resistors. So George Simon Orr established the relationship between potential difference V that is necessary for a current to flow and current. So he established that a current and potential difference are directly related. For example, if you have a 6-volt battery, then the current in the wire will be twice as much as it would be in a 3-volt battery. And for example, you can understand this comparing this to a river. If you have a river that in which both ends are the same level, then there's not going to be much flow. And however, if one of the ends of the river is much higher than the other end because of gravity, then the flow is going to be much greater. In the same way, if you have a battery, if there is much potential difference between the two ends, then there's going to be much more current. And if there's not much potential difference, then there's not going to be any much current. So another thing that you need to know is that the exact amount of current flowing in a wire does not only depend on the voltage of the wire, but also on the resistance that it provides. For example, imagine in the river that we were talking about, imagine if there were many rocks in the middle, then that would decrease the flow. In the same way, resistance is offered in circuits in order to reduce the flow. And therefore, the higher resistance, the less current for a given voltage that we're going to have in a circuit. And this establishes the relationship that resistance and current are inversely proportional. Thus, the equation R equals V over I, where R is the resistance, V is the potential difference, and I is the current. Or the equation that we're going to be using, and that is the most effective one, which is the same one as the other one, just written in different terms, is V, or the potential difference, is equal to the current times the resistance. This equation is also known as Ohm's law, which is just a description of certain class of materials. And the unit for resistance is called the ohm, and is abbreviated by capital letter omega. And which is the unit is equal to the same as saying 1 volts over amperes. And now we go to example 18.3. So, flashlight bulb resistance. A small flashlight bulb draws 300 milliamperes from its 1.5 volt battery. A. What is the resistance of the bulb? B. If the battery becomes weak and the voltage drops to 1.2 volts, how will the current change? So in order to solve this very simple problem, we're just going to have to use Ohm's law, which, as we said before, is voltage equals current times resistance, or resistance equals voltage over current. So for the first part, they already gave us the current and the voltage. They just want us to find resistance. So resistance is going to be equal to 1.5 volts over 300 milliamperes, which 300 milliamperes is the same thing as saying 0.3 amperes. So 0.3, and this is going to tell us that the resistance is 5.0 ohms, which is written with omega. And that's the answer for part A. And in part B, they ask us to find the new resistance, the new current, if the voltage drops to 1.2 volts. So to do this, we just find that voltage, which is the new voltage is 1.2, equals current times resistance, which is 5.0. Or current is going to be equal to 1.2 over 5.0. It's going to give us 0.24 amperes. Or the same thing as saying 240 milliamperes. Either way is right. And that's just, so you solve this problem just by using Ohm's law, which is voltage equals current times resistance. So moving on, we have to take into account that all electric devices offer resistance to the flow of current, and this resistance can be given in many different ways. However, in circuits, and mainly in electronic devices, resistors are used to control the amount of current, which are given by this symbol. So there are many types of resistors that can be used in many different types of circuits. However, what we must know is that the resistors, for example, take this one into account, are color coded. So the first two digits represent the power, the value of the resistance. The second digit, the third color represents the multiplier of the resistance, and the fourth digit represents the tolerance. So here's a table for the color code that is universally used for resistors. And take this one into account. So the first digit or the first color is red, which is the number 2. The second digit, which is the second color, which is green, is 3. No, green is 5. And the multiplier, which is orange, here we can see in the table that is 10 to the third, 10 to the fourth. And then when we add this together, we're going to get that the resistance of this resistor is 25 times 10 to the fourth ohms, plus or minus 10%, which is the tolerance represented by silver. And taking this into account, we're going to do a conceptual example 18.4. So current and potential. Current I enters a resistor R as shown in this figure. A, is the potential higher at point A or point B? And B, is the current greater at point A or point B? Now in order to solve the first part, which is the potential higher at point A or point B, we gotta think of it as the analogy of the river. At a point higher above in the river, it's gonna have a higher potential, and it's always gonna flow from the top to the bottom, or from the positive to a negative. Therefore, the potential is in this case is gonna be higher at point A than at point B. And the current, we gotta take into account the conservation of charge, since the current is always gonna be steady for the whole at any point in the circuit. Then the current is gonna be the same at point A and point B. So moving on, we are in section 18.4, which is called resistivity. So experimentally, it was found that the resistance R of any wire is directly proportional to its length and inversely proportional to its cross-sectional area A. So given the equation, R equals rho times L over A. As we might know, rho is used in density. Is used to represent density in physics. Why? Because I want to confuse you. However, in this part, in this formula, it is not density, it is resistivity. The units of resistivity are ohms times meters. And I know it can be confusing, but whenever you're talking about electricity, resistance, and current, anything that has to do with electricity, then rho is going to represent resistivity. And the typical values of resistivity for many types of materials are given in this table. And as you can see, one of the factors that may affect resistivity is temperature coefficient. So now we go to example 18.5, speaker wires. Suppose you want to connect your stereo to your remote speakers, as shown in this figure right here. A, if each wire must be 20 meters long, what diameter copper wire should you use to keep the resistance less than 0.10 ohms per wire? And B, if the current to each speaker is 4.0 amperes, what is the potential difference or voltage drop across each wire? So here are all the values that are given. So the length of the wire is 20 meters. The resistance can be no more than 0.10 ohms. The current flow is 4.0 amperes, and then you might be wondering what the heck is this. So this is the resistivity of of the copper wire as shown in the table that we discussed previously. So they want us to find first in part A the diameter of the cross-sectional wire. So in order to find that, we're gonna have to use the equation. So resistance equals resistivity times L over A. And solving for area here, we get that area equals resistivity times length over R. And now why do you want to find area? Because the area is equal to pi r squared of a circle, and the diameter is equal to 2 times r. So therefore, solving for the area, we're gonna get that the area is equal to 1.68 times 10 to a negative 8 times the length 20 meters over 0.10 ohms, and the area is gonna give you 3.4 times 10 to a negative 6 meters squared. So this is the cross-sectional area, and now we gotta plug this in this equation right here, and to find the radius. So this area is gonna be equal to 3.4 times 10 to a negative 6 meters squared is gonna be equal to pi r squared. So by dividing pi by both sides over pi, we're gonna cancel this out, and by squaring both sides, we're gonna cancel this out, and we're gonna get that r is gonna be equal to this right here, which is gonna be equal to 1.04 times 10 to a negative 3 meters. And so to find the diameter, we multiply this times 2, and the diameter is gonna be equal to 2.1 times 10 to a negative 3 meters. And that's how you solve part A. And in part B, they're asking us to find the potential difference, or V. And as we know from Ohm's law, we know that a potential difference is equal to the current times the resistance, or the current that is given to us as 4.0 amperes, 4.0 times the resistance, which is 0.10 ohms. The potential difference is going to be 0.40 volts. And like that, you solve part B. And now we go to conceptual example 18.6. Stretching changes resistance. A wire of resistance R is stretched uniformly until it is twice its original length. What happens to its resistance? So to solve this example, we're gonna have to know that the volume is gonna be constant always, and that the volume is equal to the area times the length. So if the length L doubles, then the cross-sectional area A is halved because they are inversely proportional. And therefore, given an example 18.3, which is the equation for resistance and resistivity, we can see that the resistance is gonna increase by a factor of 4. Now we're gonna go into section 18.5, which is electric power. So as a useful application of electric currents and electric energy, which is what we're learning, is that it can be transformed into different types of energy. For example, motors can transform electric energy into mechanical energy and thus produce work. And then electric heaters, stoves, hair dryers can transform electric energy into thermal energy. So the rate at which this energy is transformed is the power of is electric power. And in order to find the electric power, we're gonna have to know that the energy transformed of an electric current when a charge moves through a potential difference is the charge times the potential difference, therefore given by the equation Q times V. And the power is at the rate of which the rate at which the energy is transformed. Therefore, the power equals Q times V over T. So the charge is the charge that flows per second. So Q over T is simply the electric current as we had defined before. Therefore, this can be simplified as that the P, power, equals to the current Q over T times V, which is the potential difference. And this relation gives us the power transformed by any device where I is the current passing through it and V is the potential difference across it. And this also gives the power delivered by any battery. And the SI unit of power of electric power is the same as any other power, which is the watt or a 1 joule per second. And the rate of the power of a resistance can also be given in two other different ways. Because of this proofs, we can see that power equals P equals current times V, and V equals resistance times current. Therefore, we can see that power can also be given as current squared or I squared times R, resistance, or that power can be given as potential difference squared over resistance, or V squared over R. And any of these three equations can be useful when solving electric power problems. So, using these equations, we're going to be able to solve the examples. So, example 18.8, headlights. Calculate the resistance of a 40-watt automobile headlight designed for 12 volts. So here in this example, they're giving us they want us to find the resistance of the headlights. They're giving us the power, which is 40 watts, and the potential difference, which is 12 volts. So because of the equations that we learned earlier, we know that that power is going to be equal to potential difference squared over resistance, or that resistance is going to be equal to potential difference squared over power. And therefore, just plugging in the values that they gave us, we're going to find that resistance is going to be equal to 12 volts squared over 40. And this is just going to be equal to 3.6 ohms. And like that, we're going to find the resistance. So you might be thinking that you want to apply these concepts to your current life. So, for example, you might be thinking how much the electric company charges you for energy every month. However, the company does not charge you for the power that you use. It charges you for the energy that you use. And if you want to find the energy using the power, then you just have to multiply the time that you use the energy for to the power. And the companies usually charge like much larger units, such as the kilowatt hour. So 1 kilowatt hour is equal to 1,000 watts times 3,600 seconds, or 3.6 times 10 to the 6 joules. And so taking this into account, we're gonna do example 18.9. Electric heater. An electric heater draws a steady 15 amperes on a 120 volt line. How much power does it require, and how much does it cost per month, that means 30 days, if it operates 3 hours per day and the electric company charges 9.2 cents per kilowatt hour? So these are the variables that are given. Current is equal to 15 amperes, voltage is equal to 120 volts, the time that is consumed is given 30 days, and it tells that each day it's 3 hours, therefore 90 hours. They're asking us to find the power and the cost, and they tell us that each kilowatt hour they charge $0.092 or 9.2 cents. Therefore, the first thing that we're gonna do is we're gonna find the power, and we know that power is equal to current times voltage, which are both given. So 15 times 120 equals 1,800 watts, or 1.8 kilowatts. And we're gonna wanna use this. So this is our answer for the power in SI units, and we're gonna wanna use this to find the cost because it's given in kilowatts per hour. So in order to find the cost, we just wanna multiply the the power consumed, which is 1.8 kilowatts, times the time it was consumed, so 90 hours, times the cost, so it is 0.092 per kilowatt per hour dollars. And this, we're gonna see that this units are gonna cancel out, and we're just gonna have the dollars, which is the cost, which is gonna give us 1.8 times 90 times 0.092 is gonna give us $15, and that is the cost. And those are the two answers for this example. And with that example, we finish everything that the AP exam covers in chapter 18, which are sections 1 through 5.